And it's my great pleasure to introduce Drazen Adamovich, who's going to tell us about on the representation theory of affine vertex algebra on conformal and collapsing levels.
Thank you, Tomoyuki. I would like to thank Slava Futordi to invitation to this workshop in Brazil. This is my first visit to Brazil and Sao Paulo. And yesterday we had many talks of people from Brazil, and I'm impressed with the school you are developing here. So this will be a great thing for the theory, this development in Brazil of vertex algebra. Okay, and then now I will speak about the representation, certain aspect on the representation theory of affine vertex algebras. And this is really huge topic, as we heard yesterday in Tomoyuki talk and some other talks. So this is very huge developing story. Some problems are finished. There are so many new problems opened, and this is a nice thing to work somehow in this area. Okay, so what is the main subject? Main subject is always representation theory of affine VOS, affine vertex operator algebra. So as we learned yesterday from Tomoyuki, we have two natural candidates for investigation: this universal affine algebra and the representation theory of this universal affine algebra is almost the same as representation theory of affine Kac-Moody algebra, restricted representation of affine Kac-Moody algebra, but motivated by certain other aspects coming from various fields, maybe even with physical aspects and conformal field theoretic and tensor category aspects. And so it is important to study representation theory of this simple affine vertex algebra. So I'm studying this almost forever. So this was topic of my PhD even. Then it was completely new stuff. Then we in Zagreb somehow studied this as a part of the representation theory, and then this subject grew up very much, especially recently when Tomoyuki proved certain our conjecture about this representation theory of admissible affine vertex operator algebra. Okay, but we are in 2022. So now we have some new concept and new problems, and I will speak about something which appeared relatively recently about this story about collapsing levels, which also are developing in Brazil by Jetro in collaboration with Tomoyuki and Ann. But so mainly I will be focused on the idea how W algebra, which is supposed to be much more complicated objects than affine algebra, which really are complicated, can be useful in study affine algebra. So, but of course, this collapsing level will mean that on certain special levels, this representation theory, this W algebra very much simplify, and information from this W algebra can be used in study representation theory. And what is next problem? And next problem is how to go beyond admissible case and try to get something which we have for admissible. For a step, we study category of ordinary module, also called Kažan-Lušnik category for K beyond admissible. And then there are certain new concept also appearing in this direction. So this is concept of free field realization motivated by finding so-called inverses of quantum Hamiltonian reduction. I have a paper with Thomas and Naoki about the SL3 realization. And I spoke about that in Rio conference. Then I speak online. So thanks to Jetro and Raimundo. So I was speaking about this. So mainly I will skip this part, and since this is related to this relaxed category, which I discussed in Tomoyuki talk yesterday. So mainly I will describe two possible problems which I was focused last few years. One is construction of this collapsing and conformal levels. This is very much related topics. And second is how to use this in the representation theory. In the representation theory is, of course, our ultimate goal. How to apply this here. So let me. So we have. I will just recall. We start from the simply superalgebra. So here I will allow to G be Lie superalgebra, which is definitely more complicated, especially from the semi-simplicity point of view, because in Lie superalgebra we know that even finite dimensional representation, except OSP 1n, need not to be semi-simple. And then we have affinization. And then we have this guy, universal affine algebra. And this is also a special kind of high-state representation, induced high-state representation for affine Lie algebra. And we have this famous simple quotient, which we are looking now. And when physicists speak about conformal field theory of affine associated to certain level, they always think, as I understand, on this simple quotient affine Lie algebra. So if you look older paper and see notation GK, I think it means to be simple affine vertex algebra. And then what is outside of critical level, we have Sugawara-Virasoro vector. So Sugawara-Virasoro vector. This is just affinization of Casimir operator. And it has specific central charge. This is K, superdimension of G over K plus H check. And next concept is very natural, but very important. If we have two VOS, so I said VOS because we fix conformal vectors. With two conformal vectors, we say that one VOS is conformally embedded into second if conformal vector coincides. So miracle about conformal embedding is to get that conformal vector or some relatively different object coincides. And then we use some concept to study representation theory. So if there is some question, you can stop me. So just we have one VOS, another VOS, and one VOS. They need to share conformal vector. There are stronger notion, maybe some stronger, that they can share some superconformal vector or some W algebra vector, but this is, I will speak about this simple situation. Okay. And now we go in different world of W algebra, which are, as I mentioned, by definition, more complicated. I will just say information, just without details. So if you take any nilpotent element in G and K and C, and one can associate the universal affine W algebra with KGF. We have this universal affine W algebra, and this is the quantum Hamiltonian reduction of universal. So when I put K up, I always think on universal. So this is object which is well defined and very important. And then we consider simple quotient. So I assume that it has simple quotient. So it is for non-critical K, definitely. And then this W algebra. So this is ideal for investigating this looks like this. And here, on conformal weight 1, there is one affine, not for principal, but so I assume that we have generator of W algebra, of universal W algebra at conformal weight 1, and they define certain affine VOA. So we have affine VOA, and this affine VOA, it can be just some VOA associated to one Lie algebra, to tensor product of Lie algebra or Lie superalgebra. It can be some reductive, non-reductive, everything. For example, in the simple case, if F is so-called minimal nilpotent, we have a situation like we have generator at conformal weight 1 here, then we have some generator at conformal weight 3/2, G's generator, and extra generator, extra generator which generates a Virasoro algebra. This is in special case, which is maybe simple, but similar happen in other cases. I will discuss some of them. And now of course, this in universal, this affine vertex algebra is not conformal embedded. So in the universal, they are definitely not conformal embedded. But then we have here this Sugawara Virasoro element, and they're different. One is living in this affine part, the second is living in universal. They're different, but in the simple quotient, then we consider simple quotient, and then in this simple quotient, we can have that this LG equals to L. And this is the case. This is the case of formal embedding. And now, so if this happened, then we say that this affine vertex algebra is conformally embedded. And I really say that we say that this K is conformal level. So level is conformal depending on the F, but I don't mention F. Depending on F, that level is conformal. If affine algebra is conformally embedding, this exactly means that this difference here, lives in maximal ideal in this universal vertex algebra. So this means, and this is the check. So we have notion of conformal, and what is a collapsing level? This is defined above. So what also can happen? We observe this in the case of minimal algebra, that we have totally collapsing. That we just have that this W algebra is nothing else than this affine algebra. So in the quotient, everything disappears except affine generator. So this level is called collapsing. And this is case where we can use this something in the representation theory. And note that it's obvious that each collapsing level must be conformal. And one of strategy for the other, but one strategy of classification of collapsing levels, you first classify conformal, and then look which conformal level is collapsing. Well, this is essentially our way how we did, and the main tool is just check if this difference is in maximal ideal. But it can be complicated. And now, so as I mentioned, we are 2022. So I want to discuss something which appeared so much in last decade. So in the case of minimal nilpotent element, we classify this collapsing level for minimal case. So in the case of minimal nilpotent, for algebra which looks like this, we have full classification of conformal and collapsing level using this OPE or lambda bracket formula. How do you like? And then, a general case I recently studied by Arakawa, Van Ekeren, and Almoro, if I understand, for K admissible mostly. By using different technique, we try to study general case in some special case, like hook and rectangular case, which I will mention something about it. And what is missing generally, this nice formula for OPE, which we have in this minimal case. We have nice OPE. In general, this OPE is much more complicated, and essentially we try to get something without complete knowledge of OPE. So this is some of that. And but with explicit knowledge of this OPE, we get some collapsing level. Recently, joint work with Perche Vukorepa. Justine Pascal also presented some result about collapsing level. And there are probably more cases. So when you study some algebra and use computer and write lambda bracket, you can recognize what are collapsing level. Not problem is how to do this in general. So I will skip this computational part. So just try to get something very general by other methods. And let me just recall our result in the case of minimal. So what happened with minimal? In the minimal case, we have Virasoro, and this Virasoro has central charge element, and central charge formula for central charge is expressed as a ball. So this is K. I need to add K. K is missing in the formula. So K is super dimension G over K plus H check minus 6K plus H check minus 4. This is Katsukimoto obtained this formula. And then, so this is the central charge of this Virasoro element, which is known. And then we have central charge, and we have central charge of this Sugawara Virasoro, which was also written before on the slides. We have two numbers. And so if we want to have conformal embedding, we obviously need to require, this is necessary condition, that these two numbers coincide. Central charge for the affine subalgebra and central charge for the W algebra must coincide. But the question is if can we show opposite claim that if central charge coincide, then we have conformal embedding. This was non-trivial question. So if we just check numerically that these two numbers are the same, do we know that we are in the case of conformal embedding? And we did this in the minimal case. So we prove that if central charges coincides, then we are in the language of conformal embedding. So we definitely saw the equality of central charge gives you conformal embedding, but proof was somehow obtained very specially about minimal. What is the problem with minimal? Minimal, you have explicit formula, and then you use this formula. And so in our formula, we use this formula, and then we need to solve one equation, and then get some solution. And then we have two possibilities. One possibility is that level is collapsing, that everything collapses. And second is it's not collapsing. That it's not collapsing. And we give answer that level will be conformal and non. If it is conformal and non-collapsing, there are two possibilities written here. And it will be collapsing if and only if certain P of k is 0 for certain quadratic polynomials, which can be read from your P. So, and then we have complete decision if certain level is collapsing or conformal or just conformal without collapsing. And this is the formula for such elements. It works for each Lie superalgebra. So you see that they are quadratic, and of course it includes also all Lie algebra. Just put n equals to 0 in the first part of the table. You get that collapsing level for SLM are -1 and minus m over 2. This means minus h check over 2, and this is complete list. Complete list in the minimal case of collapsing level, and all other are conformal. In all other cases, we don't have collapsing. So this is the answer. And now we want to have something of this in general, without knowledge of the OPE, and we prove the following result. This appeared last month, I think. So I look in the paper. It's a slightly different version, but I adopted it for minimal. We wrote some condition in general for embedding to any vertex operator algebra. But what is general strategy? So we start with universal affine W algebra. So we start with this universal W algebra, and the first problem is calculate central charge. This is not easy essentially. This can be required certain, but this is computational problem. You have certain data, and then you calculate central charge. And then you have take L conformal vector. And then you need to have affine algebra inside. Like in minimal case, in many other cases, we have affine algebra. And with certain very mild assumption, we could prove that equality of central charge gives you conformal embedding. So these are conditions. So if algebra is generated by this difference of these two guys, two Virasoro vector, union with certain homogeneous vectors. So this can be this S set of generators can be very complicated. Usually you don't know explicitly so much about them. So this is certain one, but we need to check just this condition. Just this condition that L minus L G natural second product of X is 0 for each X of conformal weight 2. If you check this, then we get conformal embedding. So under this condition, we can prove that affine algebra is conformally embedding, and this condition works in almost all examples which we study. This condition, so we just need to. No, this is possible. They're always, so this is very, very mild. So if you see this, so for example, if you know that all generators are primary, they are definitely holes. They are singular vector for L. So it should be very. We don't. So I don't know. Possibly we don't need any restriction, but this is mathematics. Never know that it can be maybe. So as I mentioned, this is written. Story about the proof was using Hermitian form, and we use and then we just check. This was the condition to show that this vector L minus L G natural generates a proper ideal in universal affine algebra. And then go to quotient, and we have conformal image. So this is the equality of set. We always wanted to do that, and this is somehow by the book. So just check equality of central charge, and you know that in the case of conformal embedding. And let me just give one example. So I already discussed about minimal, and you can go in many directions for the linear, but first natural generalization is our hook W algebra. A hook type. So we take algebra. This is for hook of type A. This is for hook of type A, and there are super hook, but just for this classical type. We take Lie algebra SLM plus N, and then we need to associate one nilpotent element. We need to give partition of M plus N, and this partition is give M plus 1 plus 1 plus 1. So partition is M plus N is M plus 1 plus 1. And then for this partition, we have nilpotent element Fmn. And then hook algebra is obtained by the reduction of, so we take minimal, we take this element and take affine algebra on level K and apply reduction, and we get hook W algebra. And what is the structure of this hook? I don't have on the slides, but this is so this picture is somehow deformed, but not very much. Not very much. What we have this? So picture about universal hook. So for GSLN plus N. So we have G natural is here. We have G natural is JLN. G natural is JLN. And then we have, so in the minimal case, we have generators of conformal, primary generators conformal way 3/2. And here we have generators, we have also G generators, odd conformal weight G plus and G minus I at conformal weight M plus 1 over 2. So notice for M equals to 2 is 3/2. So for M equals 2, this is minimal. And then we have something extra. Then we have L. But we have then some other W algebra generator. And somewhere here is WM. So this is somehow structured. So this is more complicated. We don't have just Virasoro. We have some W algebra. We even don't know explicitly if these generators are primary, but we can take the quasi-primary. So this is the structure. This is the structure of this hook, and one can check that everything holds for this in this hook case. And we just apply our numerical criterion, and then get 4 families of level. This is for us just an example, but it should work. We didn't study much more. We also study rectangular case here, but strategy is if you know central charge, if you know the structure, then you check, and we get to 4 family. 4 family, and K1, K2, and K4, and we can check that this level K3, Mn, and K4 are collapsing. I won't give details, but this is not so complicated. But this is similar happening if you're in this minimal case. In this minimal case, this corresponds to first table. So we have two collapsing level, and two non-collapsing. And here we get, so for two, we know that they are collapsing. So by certain, but question is what will happen with this first two series of level. And this is a very interesting example which we couldn't solve all details about that. And we have formula. Insert m equals to 2. M equals 2 in this formula, we get exactly formula like in the minimal case. So, and then what happened? Now, next job is how to investigate this K1 and K2 in this case. And let me just give some comments. So, as I mentioned, this m equals 2 case gives you minimal. So minimal is solved. So we need to go beyond minimal. And we know that this K3 and K4 are collapsing, and we can prove that first two are non-collapsing only for admissible. So what are admissible levels? Tomoyuki defined yesterday, and was a discussion on several talks about. So if level K, Mn1 or 2 are admissible, we can prove by certain techniques that they are not collapsing. But we conjecture that in the first case, we will always get non-collapsing level. But in the second, sometimes we get collapsing, sometimes it's not, which is very much different than in the case of minimum. So this is somehow some numerical data. But when you give some numerical data for vertex algebra, this is the vertex algebra at each level has its own life. So it can be important for every. So some algebra are more important, some algebra are not. So some of such level are really important. I will see one. For example, first case of this first series, which we can prove, even we know that this is admissible, but we can prove that they are non-collapsing by using following result, which we proved with Thomas, Nauki, General, Zhangbang. We proved that this in this case, when take Kp, so take n is equals to p minus 1, and m equals to p minus 1, and n equals to 2. Then the affine algebra is very nice. It is L minus 2 plus 1p algebra associated to GL2. So this is SL2 times Heisenberg. And we proved that this W algebra, WK p minus 1, 2 is just certain RP algebra. And this RP algebra is coming from this logarithmic vertex algebra. They are very close. What we discussed unofficially here. So how to get this algebra? Just to mention, for people who knows about logarithmic. So there is a story about this is called doublet algebra, and then we have triplet algebra, which is Z2 orbifold of the doublet, and then we apply, and then we have so-called VP algebra, which you obtain like inverse of quantum Hamiltonian reduction. Here, we proved this exactly, and then we tensor with this certain lattice VOA and take U1 orbifold. This is about. somehow. So this completely belongs to this orbit, this logarithmic point of view. And one can easily see from this story, so this is infinite direct sum of SL2 module tensor with something here, that the composition is different, so we are very far from collapsing. So by this explicit realization, we are immediately see that we don't get collapsing. But, so according to minimal philosophy, the second series also should give something non-collapsing, but no. So then we consider level minus 3p minus 1 plus 1p. What is also similar here, that G natural is again SL2 on the same level. And then we produce one contradiction with tensor product category theory. Producing one contradiction with tensor product category theory, you can see in our paper, we can discuss, we prove that this level must be collapsing. So to be non-collapsing will be contradicting with some fusion rules, which must hold. Okay. But so we see that the second series is much more. So probably there are much more cases which can be covered, but we don't know a result from the tensor category except for SL2 on such levels. And my main difference here is that this first level is admissible and the second level is not admissible. Yeah. As we discussed. So this is quantum Hamiltonian reduction, and should be quasi-Lewis by your result. Okay. Okay. And then just to show that in admissible case, we can produce complete decomposition. For inadmissible case, we can decompose, but not that this subalgebra, which is conformal embedded, is not admissible. So somehow this admissible level, one can produce some very non-trivial extension of this algebra beyond admissible. So this K1 is not admissible. One can check. So huge extension of this, and then so this is nice Syria, and we believe that like previous, if there won't be any surprise, all these guys should be simple current in the tensor category of module, and this level beyond admissible. So it seems that I'm slow. So now I'm going to second. Are there any questions? Good. Okay. I finished with this first part, and then what is second part? We want to use this concept in studying representation theory of affine algebra. So this definition of category KLK. Note that we here allow logarithmic representation. We here allow logarithmic representation, but so M is locally finite as G module. So we here also allow non-weight representation. So we allow everything non-weight, but it must be locally finite. So locally finite. And then we have category KL little k. We are module in KLK, which are module for the simple. This is much smaller category, and we are interesting in this case. What is I need to say? This is just small category representation. We can go beyond Kazan-Lushik category and get relaxed modules, many weak modules described yesterday by Tomoyuki. And what we prove here, that if G is simple Lie algebra, first in Lie algebra case, then this KLK will be semi-simple in the following cases. K is collapsing. So when K is collapsing, we immediately have that KLK is semi-simple. When this W algebra is rational. We know semi-simplicity, and if it is semi-simple certain category, which I won't specify, it is semi-simple. So this is proof for Lie algebra. And then we recently have a paper about Lie superalgebra. And then this superalgebra, we can prove that, we cannot prove that KLK is semi-simple under this condition. We can prove only semi-simplicity of this weight category. So we have this KLK fin. This is category or subcategory of KLK, just contains weight mode, so L0 mass semi-simple and Cartan algebra mass. So by using the same technique, we prove that if we know that K is collapsing or we have a rational, and note that this works only for minimal, because we can use for minimal Tom-Yuki result of non-Vanishekov homology. Then very nicely we can use this. But what is next? Maybe what I want to now discuss: how to remove this KLK fin. So we have. So under the same condition and using the similar proof, like in Lie algebra case, we can prove semi-simplicity here, but we are interested in larger category, allowing non-weight module, allowing the logarithmic module, and allowing this. And this is hard. And this is hard because theory of Lie superalgebra is not easy. We need to know a lot of things about extension in this category, even finite dimensional settings. Slava is expert for this. So what is sorry? So what we prove? We prove the following result. So now we want to, assuming that we are proving semi-simplicity of the category of weight module, like in previous theorem. And how to go beyond this weight module, beyond this weight module. And so if you are in Kažan-Luščik category, modules looks like this. On the top component, we have certain G module. If M is irreducible by Joule's theory, so this M top is certain highest weight module for the Lie superalgebra. And so, assuming that we can prove that there are no extension in the category of finite dimensional G module for Lie superalgebra between all top levels appearing in the classification of modules in KLK, we can prove semi-simplicity beyond the category of weight module. So we can prove here. You see, this is the result which we presented. And so for applying this, so we need to first classify all irreducible representation in KLK, which is hard. And up to then we need to study extension in the category of module for the algebra. So so first problem is classification, and then identification this weights. So in the Lie superalgebra case, weights can be typical, atypical, atypicality 1, and so, and then study extension. Surprisingly, they are not completely solved problem of all extension. Maybe we didn't notice about this, even finite dimensional superalgebra. And then let me present one example. We just apply this for example. This is SLM/1, Lie superalgebra, which also appeared yesterday. SLM/n appeared yesterday, so SLM/1. And then what we need? We need to prove that there are no extension between between module for the simple algebra. So we know that in the category of 8 module, this category is semi-simple. And then we classify a representation and get that we can only get so-called single atypical module. And then there's one paper by Germoni from 1998. And by miracle, he has a result that for a typical module, for single atypical module, there are no extension. And by using this Germani result, we can prove that there are no logarithmic, not wave modules, so all category is semi-simple. And second example, SL2/1. SL2/1, so this is simple, but not -1, not level -1. But then take this spatial level, -n+1 over n+2. And then in this case, W algebra is just n equals 2 superconformal algebra, which is rational by my old result from 2001. So this is rational. And then we again have semi-simplicity of we can use semi-simplicity by the following thing. But there is, so what is the problem? Problem with SL2/1 is that even part of this SL2/1 is reductive. So it contains center. And this center generates one Heisenberg. How to prove that this Heisenberg must act semi-simple? There are no law in the representation theory. For Heisenberg algebra, you can get everything. But we included this center in one regular vertex operator algebra obtained before. So these generators belong to something bigger, for which we know that it acts semi-simple, and combining result we can prove here. And then finally, so this is the case, but this superalgebra case is much different. So here in very special level, we could prove semi-simplicity. But we can expect what is maybe more interesting, non-semi-simple category. So example, which is very natural for this superalgebra to have non-semi-simple category. So in the Lie algebra case, level 1 for level 1 affine. So if G is Lie algebra, then we have that LK is rational. But if we take this our algebra SLM/1, then LJ is not rational, even not semi-simple. Even non-semi-simple. And how to prove that they're not semi-simple? Here we have free field realization. And we have free field realization. We have one copy of beta-gamma system or Weyl vertex algebra with m copies of BC system. And then we localize beta-gamma system. We get our pi 0. And in this localization, we have inverse. We have inverses. And if we put here, and we get formula for one highest weight vector and get indecomposable module. By explicit realization, we can get indecomposable module. So even more better case, level 1 SL/1 gives you non-semi-simple category. So everything is possible to investigate here, projective cover, and so. And similar, and we can extend this for each k by knowing one result that we know generator of maxima ideal of this universal affine algebra, and we can prove that in this case category is non-semi-simple for each k positive integer. For each k positive integer, this category is semi-simple, but you notice that for the category for negative is semi-simple. So now basic question is classification is how what will be final answer? When category will be semisimple and when category won't be semisimple. In Lie algebra cases, we mostly expect semisimplicity.
So this case is not C2 final?
No.
No.
No. So no, it's not C2. So you have in the case you can see here from this realization. So level 1 SLM/1 is tensor product of beta gamma tensor with the Clifford algebra, and this beta gamma has plenty of representation. So you have infinitely many. So they are not C2 cofinite, but yes, this is it has one rational. So in this case, really what happened? So we have LK SLM, which is rational, is somehow included in this LK SLM, which is non-rational. But commutant is huge. So this is commutant, and all algebra is nothing. There are infinitely many highest weight modules. There are infinitely many modules which are responsible for non-semisimplicity, and this. I think this is very good tensor category for investigation, for various points of view. This is somehow baby example of this SLM/1 is GL1. So there is one algebra also very popular, GL1/1. And so also one can see that in this case there are infinitely many reducible, they are in the composable module, they are projective covered. And very natural next candidate will be this SLM/1 on this in these cases. And we go in the world of these non-semisimple categories. So in the super case, one can expect that even this category of Kazan-Lushik ordinary modules categories non-semisimple, so it would be nice to have a result about quantum group correspondence or something. In this case, so they're not quasi-Lies also. And what we expect, they're almost true that it should be right, that in the SL2/1, that this KLK will be semisimple if and only if K is -1. Surprisingly, here is K -1 is critical level, but it can be. This proof works for critical level. Critical cases. But like in affine case, KLK is semisimple for SL2 at least. Category. So category O, in all cases, category O won't be semisimple. But for Kazan-Lushik category, we just allow finite dimensional representation at the top. So we get so category KLK will be semisimple, category O won't be semisimple. And of course, the last category is very far. But this category, okay? Yes. So what is in this case? In this case, we have this LK SL2 included in LK SL2/1, and this K is admissible, but not arbitrary. It's very special. This admissible with properties. So our main tool was to proving that. So we know that by Hamiltonian reduction, we go here to a rational n equals 2 algebra. And then using our result, we can prove semisimplicity here. Semisimplicity here, this is the main tool. But yes, somehow this algebra SL2/1 is built from one admissible SL2, and this D algebra, which I mentioned before, which is also appeared recently. This is some algebra obtained some by generalization, some Kazama-Suzuki construction, and then but we are almost sure that what happened on the level 1. only what happened on the level 1, on each other level, we also expect that there are no reason that such algebra will be semi-simple. But still, we cannot prove. And similar story should be for other algebra. But what is the problem for other algebra? For the other algebra, so if we take, for example, for SLM/1, we know certain rationality for principle. But we are not aware of a result about rationality for minimal, which we use here. But so far, we cannot use principal reduction in this case. So this is the conjecture. And the literature, which I already mentioned. So there are two new papers, and everything happened in the last few years. Okay, thank you very much.
Are there any questions or comment? Yes, sir.
Yeah, so you had a theorem on semisimplicity of KLK that involved self-extension. Yeah, this theorem on semisimplicity of KLK thin that was in terms of self-extensions of top part.
Yeah, I can write, so I can write this theorem. So what is there are no problem with self-extension in KLK fin. When you just allow highest weight module, it's in highest weight module, and in the category must be weight. There are no problem in KLK fin. But problem can appear when you allow logarithmic representation.
Right.
And then what happened? What's happened in this case? So you consider extension. M0. So if mx is a weight module, everything is okay. But
in the sense
okay. You can formally you can add two. You can add two modules. But problem is if you allow logarithmic representation, then you can construct something like this. Semisimple L0 minus semisimple pi. And this is operator which acts on Mx. And from this you can easily see that you can allow only self-extension. So we need to exclude that there are not self-extension, logarithmic or non-weight self-extension.
Yeah, I mean, I guess I was just going to ask, so for example, for triplet algebra, of course, there are cases where there are no self-extensions of top level, but there are self-extensions. Yeah. And somehow this doesn't happen for these vertex algebras you consider. So it's general affine algebra, or just when you take category of weight
I
modules?
understand. So this is very good question and very good remark. So what is our main use, which I didn't maybe mention details. So we are in the following situation. In all theorems, which I mentioned here, so in all theorems, our main tool is to prove that each highest weight LKG module is irreducible. So we use everything here. So this is what we check by using quantum Hamiltonian reduction, that each highest weight module must be reducible. And this, together with the result of self-extension, gives semisimplicity. But in the triplet case, you have highest weight modules which are not irreducible.
Right.
You have highest weight module. Some general, what is highest weight module for W algebra? But this condition, so triplet case, condition 1 does not hold. So because of that, that each highest weight module is irreducible.
So direct sums does not preserve the highest weight?
Direct sum is not highest weight.
Not on, the sum is not highest weight.
This is a condition on, so I can't read. So this is that
Each highest weight module
for what?
for affine VOA
Oh, for the affine.
must be reducible. So this is what we use in this theorem. So this we check. This was our main tool, and with this condition, everything becomes. So this is essentially vertex algebraic contribution to the theory because without this we cannot prove complete reducibility. So this is what we check. And in triplet case, you have plenty of. So you have lattice VOA included. It is obviously non. But also it's question about triplet or singlet. Can you maybe define one smaller category, which can be semisimple? I don't think that. So all categories is not semisimple. All categories C1 cofinite module are not semisimple, but maybe I think some smaller category could be still. Could be. You just need somehow to exclude non-irreducible highest weight module somehow. But here is okay.
Can I ask something just conjectural related to Jeff's question? Well, I'm not sure if it's related, but do you have a guess whether there might exist a simple vertex algebra set with self-extensions of simple modules, so non-trivial self-extensions of simple modules, and this vertex algebra be reasonable, say C2 cofinite. So the triplet gets close to this. It has non-trivial extensions, but it doesn't have non-trivial self-extensions.
But is it a symplectic fermion? So Z-graded. So I'm not. So if you consider symplectic fermion, it is C2. It is not vertex operator order. This is Z-graded. So it is Z-graded. Z-graded super vertex operator algebra. And then this symplectic fermion. Symplectic fermion, that's almost holomorphic, like we discussed liquid acid. So almost holomorphic. There's only one irreducible module. The C2 cofinite, but they are non. But again, for this symplectic fermion, we have in the composable module. But logarithmic module, projective cover, then you include in this logarithmic module, and I think this is self. This is, but that in the case of, so in the logarithmic module, I think this is self-extension. But this is the only example I know. For vertex operator algebra, I don't know. So this is not strictly speaking vertex, but symplectic fermion. They are they have logarithmic self-extension. So this is what we are afraid that maybe in the super case it can happen to get some. So still we haven't covered all possible cases. All possible cases, but so far in all cases we didn't get such self-extension. But so another thing which I mentioned somewhere, if we apply inverse of quantum Hamiltonian reduction here, we will get this n equals 4 superconformal algebra. But then you don't have then somehow you don't have such thing. Because inverse of this logarithmic representation are not in KLK. Not KLK, but Do you know some? Are you interested in some other?
No, I'm just looking for examples.
Okay.
I don't know.
I think this is the closest. So, but not.
Any other question? If not, let's thank Drazen for the nice talk.
Thank you.
So we take a coffee break and resume at 10:30.
What now? I turn off. I press. Yeah.